Okay, so good morning. Today we want to do problem solving related to Bernoulli equation, and whatever we discussed today in class is going to be on the test the next Tuesday. Yeah. So how many of you are aware that I posted suggested practice problems for both modules 2 and 3? You are aware? How many of you have actually started working on it? Good, good. I want to see more hands go up. I'm repeating myself again. If you come to the exam without practice, you will not be able to crack it. No matter how smart you are, it will require you to know some concepts which, if you had in practice, you have no other way of knowing on the test. Okay, so please practice. Did you see the mock exam that I posted? There is a mock exam. If you haven't seen it, please go take a look at it. The implication is that those 5 problems about the same difficulty you can expect in the exam. Typically, my exams, I design it like 2 problems are average. If you had been in class and you paid attention, you should be able to do them. 2 problems are generally very easy. Anybody who's looked at the textbook and has solved a few problems will be able to do those. And 1 problem will be challenging, which is for me to segregate the students who really are understanding the material and excelling from the other ones who just barely know the material. So you should expect to have 1 challenging problem and 2 average problems and 2 easy problems. That's generally the split up. Take a look at the mock exam. What I hope to see from you guys is you would attempt problems that are similar to the mock exam, not just do the 5 problems and expect to ace the test. That won't happen. But if there's a problem asking you to calculate force on a surface in the mock, the suggestion is go find similar problems from the textbook or the practice problems and do those. Okay, just doing 5 is not going to cut it. Understood? All right, I'm just setting the expectations straight. Like show up on the exam and then you didn't practice, but then you expect to do well. Don't do that. Won't happen. Okay. Any other questions about exam and practice problems? No? Okay. Yes.
So first midterm is the 24th next Tuesday, and then we have like a week and a half of class.
Yes.
The second midterm, like after spring break.
I have to check the dates, but it's coming up after. I don't know immediately after. I think it's maybe a week. You can check the dates. I don't remember.
So
Okay. Do you remember?
I think so.
What is the date?
Well, I don't know what day, but I think it's.
I know it's on syllabus. I put it on there. I'm saying it's not right after the thing.
Okay.
Yeah. What was your question?
That was it.
If there was not a question, you just said a statement.
Oh, never mind.
Okay, so in this remaining time, let's hope to do a few examples related to this Bernoulli equation. If you have your textbook in front of you, please bring that up. I'm going to pick problems. It will be easier if you have your textbook, but anyway, I'm going to project it so that people can quickly see what question we are talking about. All right, there we go. All right, we are going to do problem 3.24. Problem 3.24. I want you to take a look, make a simple sketch, and then we'll continue with the solution. make it bigger.
Do you want us to do this on the application paper or?
On your notes, there will be some conceptual questions that I will ask, and you can do those on the sheet of paper. So problem 3.24, that's what we are starting with. Towards the end of last lecture, I talked about the pitot tube and how it is used to measure velocity. This problem will illustrate that with numbers. Okay, so let's look at the sketch. There is a flow of air at 30 meters per second that is going past this pitot tube. This whole setup is called pitot tube, this arrangement. And what you see here at the bottom, that is called a manometer. It is a pressure measurement device. Sometimes it is a manometer using a liquid. Many times it is the transducer that just electronically measures it. So either case, the pressure difference created in this part of the device is measured using the manometer. Okay. So first question is, what creates the pressure difference? Now for 1 minute, feel free to look up. I'll give you time to continue. The airflow is coming from left to right in this picture at 30 meters per second. I said, please look up. I'll give you time to write. This is important. So the air is coming at 30 meters per second. Some of the air goes through the inner tube where it just takes a turn and is decelerated by the liquid here. That is, the assumption is the air is brought to rest from 30 meters per second to 0. Okay. Another fraction of the air which doesn't go through the inner tube continues to travel past the outer tube, and you can see these two holes that are drilled 90 degrees to the airflow. 90 degrees. Okay, these holes are drilled such that they are perpendicular to the airflow direction. And what happens is the gas, even though it is flowing with a velocity in this direction, the thermal motion of the molecules will ensure that gas molecules do get in here and they enter the outer tube and they are brought to rest by this liquid. So what you have here is the bulk flow with velocity 30 meters per second is brought to rest, and the thermal flow and the thermal motion, which doesn't include the bulk flow, is also brought to rest at a certain by this liquid. So this is what creates the pressure difference. Meaning, what did we learn about Bernoulli equation? That it is P plus half rho v squared plus rho gz is equal to constant. So if you think of a point here, okay, a streamline that is here with 30 meters per second velocity, and the streamline that the same streamline terminates at this point, it is brought to rest. So basically, you're going from velocity v to 0. Okay, so we are going to sketch that out and write it and mark some points and apply Bernoulli equation between 2 points. But what you want to copy from here is the sketch and the numbers so that we can get rid of this and I can write on the board. So continue, please. If you're done, I can remove this and I can write on the whiteboard. So please let me know. This is problem 3.24 in the 8th edition. I don't remember what number it is on the 9th edition. But this is, I think, one of the problems that is on the suggested practice problems. Can we remove this? Yes. Go to the solution. Are you okay? Good. Can I? Okay. All right. All right. So now I have my pitot tube, which I'm drawing here. Okay, so this we'll just focus on the inner tube for now. Okay, so the inner tube looks like this. So this is what the inner tube does. So the airflow is coming in at velocity v, where v equals 30 meter per second. And let's say we draw a streamline that basically connects up to here, where your liquid level is. This is liquid. Okay. And the other limb of the liquid goes for the outer tube, which we'll talk about. So let's call this point 1 and this as 2. Okay. So first assumption is at speeds around 30 meter per second, air may be considered incompressible, which means you can calculate a density rho, which is based on atmospheric pressure and nominal temperature. What temperature should be used? If nothing is given about temperature, what can we use? Incomplete information. You have, as the engineer, you have to make a decision. What is a reasonable choice here? There's a standard temperature, you can use that, or you can say a nominal temperature. Let's say the lab you're operating in is at 25 degrees Celsius or 70 degrees Fahrenheit or something. Just use it and state it, assuming T is 20 degrees Celsius. Just assume it. Something reasonable, that's all. Okay. And atmospheric pressure, you know what that is. So I'm going to trust that you are going to be able to do this calculation and state the density in units of kilograms per meter cube, and R would be 8.314 joules per, so not joules, joules per kg Kelvin. I'm going to let you do this calculation later. I don't want to get sucked into that. But the number will turn out to be something close to 1.2. That's what is important. We need a number. Okay. So at speeds of 30 meter per second, air may be considered incompressible with a density of around 1.2 kilograms per meter cube. And why this is okay? Why this is okay? Because 30 meter per second, if you divide by the speed of sound, which is approximately 330 meter per second, is a number that is much less than 1, which is why we think it's okay to say or think air behaves as an incompressible fluid in this context. It's all contextual. If the airspeed were 350 meter per second, what would be your conclusion? In that case, it would be 350 divided by 330, which is a number comparable to 1. So air cannot be thought of as an incompressible fluid. So your participation exercise sheet, just write this. So the speed of the flow divided by the speed of sound. This number is called Mach number. For Mach number much less than 1, the fluid may be considered incompressible. For Mach number that is comparable to 1 or greater than 1, compressibility has to be considered. And how we consider that's a separate course, we won't go there today. Compressibility must be considered. So in that case, you can't say it's incompressible. So this is what I want you to put down for your participation. One of the things was participation. First thing you learned, when is it okay to consider a fluid is incompressible versus compressible, especially for gases.
Could be that, like for fluids like water, they're, I guess, the speed of sound is so
Larger.
higher, larger that the speed of it being close to zero or whatever, it still makes the Mach number.
In a sense, yes, there is the speed of sound is higher. So think of a ship going at that speed, that's practically impossible because our propulsion systems don't really get you to that speed. That's one reason. The other reason is that for the liquid, for gases, this is strictly true. For liquids, as they get or as they move at higher speeds, more effects like viscous heating come into play. So a liquid will not remain a liquid at those conditions. It will start vaporizing and you will get like a mixture of steam and water or superheated water. So it becomes very complicated for liquids. Gases are easier to think of. That's why we don't talk too much about liquids because it's a very messy picture. All right, thank you. Good question. Okay, so all right. So first thing is we made a determination about density. All right. So let's apply Bernoulli equation between point 1 and 2. That's our goal here. At this point, the velocity is v. Okay, and the pressure is atmospheric pressure. Okay, and let's assume height difference is negligible. So the second assumption in our list is no elevation changes. So we are not going to be worried about the rho gc term for this problem because the entire assembly is only like a few centimeters. So it doesn't make much sense to worry about height differences between the 2 points. Kenzie, do you have a question?
What's the 15 meters? What does that mean?
Okay, that means the pressure and temperature must be evaluated at 1500 meters. So I told this 1.2 based on ambient conditions, atmospheric pressure conditions. For this 1500 meters, you have to look at the standard atmosphere, determine what the pressure is, and evaluate the density at that pressure.
So did you just do that for us?
I didn't do that for you. This 1.2 is mostly true at sea level. If you are 1500 meters above sea level, this will be a little lesser because air gets less denser. So you'll have to redo the calculation.
So we're solving the problem at sea level, I guess?
We are solving the problem at sea level. So we are trying to understand how to solve the problem. You can solve it at 1500 meters elevation. Okay? Good question. What else? Are we okay? Are we all together? Yes? Okay. So no elevation changes. We are not going to worry about that. So then we are going to write Bernoulli equation between points 1 and 2. At point 1, we'll call it P1 plus half rho 1 or rho V1 squared equal to P2 plus half rho V2 squared. All of Bernoulli equation problems is in this template. You have to identify 2 points and apply Bernoulli equation between those 2 points. That's the work or the procedure. Okay, so here's the cheat code for every problem in this topic. Identify 2 points and apply Bernoulli equation between those 2 points. What do we know about P1? P1 is the pressure with which the fluid approaches this pitot tube. So P1 is atmospheric pressure. Just want to make sure I don't go out of the camera. And what is V1? 30. V1 is 30 meter per second. Thank you. Okay, and what is V2? The fluid is brought to rest at the surface of the liquid. So what is V2? 0. 0. Good. So V2 is 0. And P2, okay, P2 is the pressure exerted by the fluid when all its bulk motion has been converted to thermal motion. That is, all the kinetic energy with which it came inside, it has been brought to rest and it is now only undergoing thermal or molecular motion. So all the pressure that was previously related to the motion, which is the half rho v squared, is now within this pressure. And this is what I talked about in the previous lecture. This is the stagnation pressure. So we talked about what is static pressure. Anybody can recall? What is static pressure? Put that on your participation sheet. What is stagnation pressure? What effect or what is causing stagnation pressure? Oh, sorry, static pressure. Yeah. Thermal energy or molecular motion. Please write that down. Static pressure is caused by thermal energy or molecular motion. And what is half rho v squared? We gave a name for it last lecture. Dynamic pressure. Thank you. So this is dynamic pressure, and dynamic pressure is basically is caused by the kinetic energy of the fluid bulk motion. Put that down on your sheet. Dynamic pressure is caused by the kinetic energy of fluid motion. Okay, and when all the kinetic energy due to both thermal motion and bulk motion is converted to is brought to rest, that becomes stagnation pressure. So stagnation pressure is caused by or sorry, it's not caused. Stagnation pressure represents the sum of static and dynamic pressure. It's like all bulk motion has been converted to thermal energy or thermal motion. Yes? Nobody assumed it's zero. We're still going to solve it.
So why did we zero out?
Oh, no. Okay. So this liquid level difference is different. See, this part here, the fluid that goes through the inside, think of it as it is exerting pressure over here. Okay? The fluid that is going past here, we'll talk about it. The thermal motion is sensed in the perpendicular direction, and that is what is going to be sensed here. So arguably, this contains both static and dynamic, whereas this contains only static, so this will push a little less. So that's why this liquid level is above this level. That's what we are trying to figure out. But what I meant as elevation changes is zero is like saying between this point or between the topmost point and the bottommost point, it's probably like a few centimeters. Over that few centimeters, we don't have to worry about what the pressure change would be. That's what I said, let's see. So on your sheet, make sure you have static, stagnation, and dynamic pressure. Just few words for each of those, okay, so that it reinforces. Are we good? Everybody's caught up? Some are writing, I'll wait. Okay, so this just simplifies as P atmosphere plus half rho 30 meter per second squared equals P stagnation. P stagnation. This makes sense? This is a key step. If it makes sense, we are good. Okay. And even though we say stagnation pressure, the more or a more commonly used word is total pressure because it's the total of static and dynamic. And we use the symbol PT. So we'll write PT equals P atmospheric plus half rho V squared, or P equals PT minus PA divided by rho times 2 square. I just put the symbol PT instead of P stagnation, which is kind of long and inconvenient. So I'm going to use PT to denote stagnation pressure moving forward. Okay. Done writing. Can we talk? Look up, please. So firstly, notice this equation. Okay. It says the velocity or whatever the fluid velocity is, it causes a pressure drop and it scales with pressure drop to the power half. Okay. Here's where you go from just knowing the physics to becoming an engineer. So this is 30 meter per second, right? If I quickly ask you for 30 meter per second, you're going to get some pressure drop or pressure difference between this limb and the other limb. Okay. If I make this velocity 4 times bigger, like if I ask you what will be the pressure drop or pressure difference if the velocity were 120 meter per second, what is your quick answer? This equation says velocity scales as pressure difference to the square root. If I make it 4 times, what would happen?
Double.
You will double the pressure difference. That is, whatever we don't know yet, whatever pressure difference you measure or see for 30 meter per second, for 120 meter per second, it will be twice as much. This is the kind of thinking you need to develop. It's not just you see a formula and you memorize the proportionalities. You should be able to think on your feet. What happens if I double something? Or what happens if I make something half or quarter or something? Okay. The other thing is it also scales with density to the power half. Okay. But in this case, our density is constant. The reason to think like this is when you are designing a pitot tube, you are definitely not designing it for a single velocity. An instrument is always designed for a range of velocities. Say you want to measure 0 to 150 meter per second. So then you'll have to think for 0 to 150, what range of pressure difference to expect and what manometer or what manometer fluid or what pressure transducer should I use? Because this thing or this system has two subsystems. Do you recognize that? this part creates the pressure difference and this part senses or measures the pressure difference. Do you see that? You can swap this out. You don't have to have a liquid based manometer. You can stick a pressure transducer here. It would read out pressure difference. At the end of the day, you need pressure difference. You don't care how it is measured. Is that clicking? So there are two systems here. One that is causing the pressure difference, and the other that is sensing the pressure difference. Elijah, are we okay? Christina, good? Any questions? Somebody is feeling a little confused? Good. Okay, so we have this velocity equal to 2 times square root of Pt minus Pa divided by density. All right. Now, if you know Pt and Pa, you can compute a difference. Or if you are able to measure the difference directly, you can use this velocity to compute velocity. I'm sorry, you can use this equation to compute the delta P. Because in our case, we know velocity, we are asked to calculate something else. So let me write a few notes here for you to remember. Usually, a pitot-static tube is used to sense flow velocity. Hey, where is our aviator? Do you know where he went? He has used it in his while riding a flight, I guess. So maybe he'll tell us the pitot tube is actually used to measure velocity. Okay, usually it is used to sense velocity. The pressure difference is read off of a manometer which uses a liquid or a suitable pressure transducer. In any case, if you know if you want the velocity, you have to know the pressure difference between the two, between the inner and outer flows, and divide that by the density. Now we are going to focus on this manometer. That's the second part, the sensing part. Okay. Are we good? I'm going to erase some portions. Okay. All right. The flow that enters the inner tube is brought to rest on side A. I'll call this side A and this is side B. Air is brought to rest on side A. The pressure exerted by the air on, so this is what I called point 2 here, on the surface containing two or the liquid surface is the total or stagnation pressure PT. So this side is, I'm going to label it is PT. With me so far? Okay. Now let's focus on the other flow. That is, a part of the flow goes past the inner tube. It is going on the outside. Okay. Now please take a pause. Listen to this. This is a key. This is important. In the sense, these holes. Okay. So if you have a tube, imagine punching 2 holes or 4 holes or 6 holes, or there can be many. Essentially, these holes must be drilled perpendicular to the flow. Why perpendicular? Perpendicular to the flow or perpendicular to the local flow velocity. Very good. Local flow velocity. Why?
That's not affected by velocity.
Can you say that again, please?
That doesn't like retain velocity.
So that it doesn't contain any energy due to the bulk motion. You want to isolate the molecular motion in this pressure that you are trying to sense. And if you have it at any angle other than 90 degrees, you will have some bulk kinetic energy contribution as well, which you don't want. Is that making sense? So this might sound like a very academic thing, but when you are actually using a pitot tube to read a flow velocity, or you're mounting it as a sensor in your bigger system, the important consideration is you have a sense of what is the local flow velocity and mount your sensor that is so that these holes are exactly perpendicular. And how will you ensure this in practice? It's easy to say, I can give you instruction, go mount this perpendicular to your local flow velocity. But when you're on the field, how the hell do you actually know if you have done it right? If I ask you a question like, how do you know if you have done it right? You should think, what will happen if I do it wrong? What will happen if it's not perfectly perpendicular? Think about that. What's the consequence of this not being exactly perpendicular?
Something will leak.
Sorry?
Something will leak.
No, this is not, here there is nothing to leak. So what you're doing is, let's say there is an airflow, and I imagine my hand is the pitot tube. I have to hold my hand exactly parallel to the flow so that the holes are exactly perpendicular to the flow. Now what will happen if I hold my hand at an angle and in some direction? What's the consequence of that on the pressure difference that you're going to read? It will increase the pressure, or sorry, it won't increase the pressure. It will take away some contribution from here and put it over here. Okay. So if you want to make sure that this side, okay, if you want to ensure okay, so this is the outer inner. If you want to ensure that the outer doesn't have any contribution due to bulk motion, you have to have it perpendicular. So what will happen if you don't have it perpendicular? It means there will be some contribution of the bulk motion here, which means your liquid level will be lower or higher than ideal. I'm asking you, will it be lower or higher if there is some contribution of bulk motion to this side? it will be lower. So extend that thinking, there is a perfect positioning and then there is all other imperfect positioning. What is the distinction between perfect and imperfect? The liquid level will be dash for the perfect position and will be lower for imperfect positions. The liquid level will be the highest for the perfect position. So when mounting this, when mounting a pitot tube, okay, you ideally want, I'll draw the axis of these holes, and this is your velocity, which means this direction has to be 90 degrees. This is ideal. Okay, if it were not ideal, let's see if I have another color marker. Let's say there is a small angle. Instead of redrawing the pitot tube, I am changing the angle of my velocity. Okay, if there is a small angle, theta, you can write that, or you can say that the pressure difference delta P will be maximum only when the mounting is perpendicular to the local flow velocity. Okay. All right. So now we are coming to the easy part, which is over this side it is PD, the total pressure. Over this side it is what should be this? This should be what exerts pressure at the other side of the liquid?
Yes.
Static pressure. It can sometimes be different from atmospheric pressure, but the flow is in this direction. The molecular motion, the random motion is what is causing the pressure to be sensed here. So this pressure is static pressure. In our case, static pressure is P. Okay. So this, think about this. So used to doing this on PowerPoint, I was thinking, where is the undo button? Okay, so this is PT, okay, and this is PS, PT and PS, or PA in our case, P atmosphere. That is what is causing this height difference. This height difference in the manometer is due to PT minus PS. So rho manometer times G times H equal to PT minus PS. Yes.
So that rho GH is also just equal to the pressure through the motion.
Yes, that is, we are going to use this rho mgh, manometer fluid density times G times H, for delta P here in order to compute velocity. You can, as I said, the typical usage is to use this as a velocity measurement device. In this problem, it's sort of a backward problem in the sense they give you the velocity and ask you to predict what the height difference will be. If you are in the lab, you would be reading out the height difference and use your calculator to get velocity. That's the typical usage. So from now you can take this problem home in the sense, you know there is an equation for velocity. V equals square root of 2 times Pt minus Ps divided by density. But this is 2 times the density of the manometer fluid multiplied by G times H divided by the density of air. So this V is given to be 30 meter per second. Density of air, like Kenzie said, you can compute the density based on the pressure and temperature at 1500 meters altitude. You can do that. But I just did this problem at sea level. So I'm going to say this is like 1.2 kg per meter cube. You know G, density of the manometer fluid is given to be. How do you express density? In this problem, they have given density of the manometer fluid to be specific gravity of 0.75. The specific gravity of 0.75 is like saying the density is always multiply specific gravity by 1000, the density of water. So this is like 750 kg per meter cube. And then H is the only quantity that you need to calculate. You can do that, so I'm not going to do that. Okay. What I really expect all of you to do is do the practice problems, get clarity or get stuck, and come talk to me. Unless you try something, it will be hard for me to help you. Any questions before we move on? We have another 35 minutes. Is this connecting? I mean, is this working for you? It's hard for me to gauge because you're all very quiet, but also it's a very simple problem. The reason I took some time is to tell you some nuance along the way. Like we talked about when is a fluid compressible? Based on the velocity, you make that calculation. And like he pointed out, if it were a liquid, we mostly assume it's incompressible because dealing with liquids that are moving at high speed is a very tough problem that even it's probably like a research problem. We talked about how the Pitot tube has two components, if you recognize. The sensing element, sorry, the structure that is solving the pressure difference and the transducer which is used for sensing, the manometer being the most common transducer for pressure. Now, is the manometer an analog or a digital device? Why do you say it is analog? It is not based on electronics, first of all. It's a physical instrument where a liquid responds to the pressure change. Okay. All right. So then you have the Bernoulli equation applied between point 1 and point 2. So at point 1, the fluid is with a certain velocity. At point 2, then the fluid is brought to rest, which means all the dynamic or kinetic energy is being converted into thermal motion. which gives rise to the stagnation or total pressure. So we have a way to at least connect between what is the static pressure at point 1 and what is the total pressure at point 2. With me so far? Now, if only you knew what the static pressure at point 1 is, then you can calculate the velocity. You do that by letting the flow go past, but try to sense what happens in the transverse direction. You do that by drilling holes on the outer cube. There could be 2 holes, 4, 8. There could be any number of evenly spaced holes around the circular periphery in a real device. Okay. So that those holes drilled perpendicular to the flow will sense the static pressure on the other side, so that you could read the height difference as the pressure difference between PT and PS, P total and P static. Okay, those are all things that you could expect in this course. But what you should have technically learned in fluids lab or fluid thermal design is how do you mount a pitot tube. The mounting is something that isn't trivial. On the field, it just doesn't come to you. It's easy to say theoretically it must be perpendicular, but how do you ensure that it is the correct mounting at which your pressure difference will be maximum? If it's not maximum, it means you are not there yet. So you read out the height difference that is related to the density of the manometer fluid. The density and height are related to the pressure difference, which is what appears in the Bernoulli equation as well. So the typical usage is read out the pressure difference, use it to calculate the flow velocity as a measurement instrument. But this particular problem is worded backwards. They give you the velocity and ask you to compute what would be the height difference between the two sides. Okay, so that's the sum. Yes.
Is the height difference very small?
No. Okay, what is small? How do you call something small?
I just ran the numbers for this one and I got 6.8 10 to the negative 5.
That doesn't sound correct.
Because the PT is very close to the atmosphere. Right?
I can't say for sure unless I do the calculation. But what I would say is, in this case, let's do a quick calculation. There is no other way I can answer whether that number is correct or not. All right, 30 meter per second equals 2 times density of the manometer fluid is 750, density of air is 1.2 times G is 9.8 multiplied by H. Okay. So this is about 1250. So I'm going to write 900 equals 1250 H, which means H must be about 900 divided by 1250. Let me make sure I have the units right. Think so. So this is about 3/4. 3/4 is 0.75 meters. 0.75 meters. Now that does sound like a lot. That's like 75 centimeters. So who wants to have a manometer that's 75 centimeters? But remember the original design of the problem. What was the altitude? 1500 meters. At 1500 meters, do you expect your density to be smaller or larger? Smaller, right? Yeah.
So when I did the calculation inside of the square root,
Yeah.
I got 12,250.
12,250. So I missed something. I could have. Okay. 12,250.
So then it tends to, I got 0.073.
12,250. 0.073 meters This is about 7.3 centimeters. That isn't so bad, 7.3 centimeters. Okay, thank you. All right, let's move on. I want to cover one more problem. Okay, half an hour. Let's do problem 3.50 from the book. I'll bring it up. Problem 3.50 from the 8th edition. There are at least 2 or 3 more Pitot tube problems to fix. I would strongly urge you to try those. Problem 3.50. Water flows steadily in the vertical variable area pipe as shown. Determine the flow rate if the pressure in each of the gauges reads 50 kilopascal. Determine the flow rate, not velocity, flow rate. Okay, if you're done marking the sketch, I'll tell you a strategy for all these problems. They are all kind of the same. You can have a common strategy. Okay, so here's the strategy. So in all of these problems involving Bernoulli equation, what you have to do is try to identify a line which can be called a streamline, which goes through the intended flow. In this case, you are interested in what goes on between this cross section, which is at 2 meters, and this cross section, which is at 1 meter. Okay. Let me ask you a very simple question for which you can put the answer down on your sheet. Is the flow rate the same? Is the volume flow rate the same at every section in this pipe, in this context? Is the volume flow rate same or not same? Same, put that down. If you say not same, you should first tell me why and then put that down. Is the volume flow rate constant at every section in this pipe? Anybody is want to tell why it's not the same? Yes? Do you want to say something?
I think it's
Same.
I was gonna say not the same, but I didn't hear you say volume flow rate, so I just heard flow rate and I was like,
Even if it is mass flow rate, okay, it is the same, and here's the reason. There is something we can all agree that mass is conserved, right? Whatever comes in has to go out unless there is some storage inside. What goes in has to come out. Number one. Mass coming in per time should be equal to the mass leaving per time. Now, if I say that the fluid is incompressible, which means its density is not changing, it's a constant. Density times volume flow rate is mass flow rate. So what comes in at the same density it has to leave, which means the volume flow rate also has to remain constant too. Simple. Would you agree with me? Because mass is conserved and density is constant, the Q is a common value for every cross section in this tube, number one. Okay. The next step in Bernoulli is trying to understand which are the 2 sections that you really need in this. Which are the 2 sections that you really need?
The cross sections with pressure gauges.
The cross sections with pressure gauges, because that's the only place, only 2 points where you can actually apply Bernoulli knowing the pressure. If it were anywhere else, let's say you fix some midpoint between the 2 gauges, it's useless because you don't know the pressure there. So the points of interest are the section with the gauges. Thank you. Okay. So then next step is, I can't draw it here, but next step is you identify the streamline which doesn't bend or doesn't have any kind of curvature, which would be a streamline which is kind of unaffected by the cross section change. The center, that is the one that is axially at the center, right? The central streamline, or the one that is passing through the axis of this tube, will not bend or will not change. It will just go through straight. So we are going to now, I'm going to turn this off and draw. Okay, so we have our inlet cross section and the center line. Okay, at the inlet we have a gauge, and then the inlet reduces in cross section, and you have a gauge at one more location here at the throat, and then kind of goes back. Okay, so we'll call this section 1 and this section 2. All the assumptions that you need to make for using the Bernoulli equation are already given. Like it's already told it's a steady, inviscid, or a flow without any viscous effects, and incompressible flow. All these are already told. Okay. Consider the streamline that connects points 1 and 2. 1 and 2 are on the center line. So you would write P plus half rho V squared plus rho GZ equal to constant. That's the equation. The way to apply that is saying, if you sum up P plus half rho V squared plus rho GZ at 1 and 2, they should be equal to each other. Meaning P1 plus half rho V1 squared plus rho GZ1 equal to P2 plus half rho V2 squared plus rho GZ2. Okay. Identify 2 points where you have information. Information being measurement of a pressure at those points, and apply Bernoulli equation between those 2 points. What is the prime requirement for applying Bernoulli equation between the 2 points? They must lie on the same streamline. If that fails, you got nothing. Meaning, let's say you take a point here and you take another point here, you can't apply it between 1 and 3. You have to apply it between 2 points which are connected by a single streamline. You can't have something that jumps, in the sense this goes something like this. If you started here You started in Minneapolis, you can apply it in Memphis or New Orleans. You can't do this in Colorado. That makes sense? You can't jump streamlines. What I meant by Minneapolis is the river Mississippi. It starts near Minneapolis, flows down to St. Louis, Memphis, and New Orleans. You know this. So you can apply it between 2 points which are connected by the same streamline. But you can't apply it between a point and another point which are not connected by the same streamline. You can't jump across streamlines. Okay. So what is P1? Is the information known from the problem statement?
50 kilopascals.
50 kilopascal. Thank you. 50 kilopascal plus half rho for water, which we know is like 1000 kg per meter cube. Okay. 1000 kg per meter cube. Yes,
P1 and P2 just cancel out because they're both.
they are going to. Perfect. So then you have V1, which you don't know, we'll just leave it as V1 squared plus rho G. What is Z1? What is the height difference between the 2 points from the diagram? 10 meters, right? The height difference is 10 meters. Okay. And I can measure height from any plane. I can call this plane Z equal to 0, or in other words, I can say Z1 and Z2 here, and Z2 minus Z1 would be 10 meters. Okay, so instead of writing rho G Z1, I'll just write this is equal to 50 kilopascal again for P2 plus half rho V2 squared plus rho G Z2 minus Z1. Okay, so why I wrote 50 kilopascal here again is P2 is also given to be 50 kilopascal. Okay, that cancels out, and this is 10 meters. Z2 minus Z1 is 10 meters. Okay, and instead of writing rho, I'll just write it as half rho V1 squared. So I have half rho V1 squared minus V2 squared equal to rho G. I'll call this delta Z. I told you I don't like putting numbers in the middle. I'll just use symbols. Are we good so far? Yes? No? Alright. So density cancels out. Okay. So I have V1 squared minus V2 squared equal to 2 times G times delta Z. We call this equation 1. Okay, that is not enough to solve for V1 or V2. Okay, we still need one more equation obviously, but let me ask you, do you see that V1 and V2 cannot be the same? Right? The fluid has to accelerate because if you are at a movie theater and there is just one exit and everybody is trying to leave, we are all squeezing through. So you have the density either accumulates there or you have to move fast out of there. Of course, this is incompressible fluid, which means the density cannot increase. So the fluid has to leave faster in order for everybody to leave. Okay? Yes.
That's why when I thought you just said flow rate, why I was like confused. No one agreed that it was unchanged.
See, for a person, it has to be incompressible. You can't like squeeze people onto each other. But
Yeah.
fluid molecules can be compressed.
Well, I was saying like, my brain when it's just flow rate was thinking velocity. So when you said volume flow rate again, that's when,
So volume flow rate is, what is volume flow rate? It is velocity multiplied by area, cross section area.
Yeah.
So since cross section has reduced compared to here, so what we know is Q1 is same as Q2, we know that. Q1 equal to Q2, we'll call it Q. That's what we are trying to calculate. And Q1 is velocity 1 times area 1 equal to velocity 2 times area 2. And since area 2 is smaller, velocity 2 has to be bigger. That's all I'm saying. Okay, so we'll write V2 is V1 times the area ratio. We get our second equation now. So I'm going to use this expression for V1 over here. Sorry, expression for V2 over there. So this is V1 squared minus V1 squared times area ratio squared equal to 2 times G times delta Z. Okay, so further continuing, V1 equal to 2 times G times delta Z divided by 1 minus A1 over A2 squared, the whole thing squared. Look at this and make sure you understand the algebra and tell me if it's okay. Are we okay? Okay, this is velocity at cross section 1. And if you wanted the velocity at the throat, we call this throat the cross section of, the lowest cross section. If you want the velocity here, you can simply take V1 and use the area ratio to get V2. Okay, the problem asks for Q. It doesn't stop with V, it asks for Q. So Q can be written as V1 A1, which would be A1 times square root of this expression 2G delta C divided by 1 minus A1 over A2 squared. If you had seen, open the file for the mock exam, on the top I wrote, provide all the steps, 85% of the credit for the steps and 15% for final answer. If this problem appears and asks for the flow rate, the actual number in meter cube per second or whatever, that carries no more than 15% weightage. It might be even lesser. But if any of you got up to here, done everything conceptually correct, and messed up only the final number punching, you will probably lose only 10% of the points if you had all the steps down. But if you gave me nothing, because on the exam sheet you just put a number and that number is wrong, you will probably end up with a 0. So that is why it's very important you work it out methodically. And not only that, you tell me that you have worked it out methodically. You write everything carefully down, any assumptions you justify, and keep it clean and bring it to a point where you have an algebraic expression, then put numbers in. Don't do the numbers at the beginning. Okay? Questions? So you will do the number substitution. I'm not going to do that. Okay, we have 10 minutes. I would like to do one more problem if that's okay. Have one selected. All right, problem 3.47. Problem 3.47. That soda can I got it. So think of this can of soda if it was full, and instead of opening at the top, you are in a hurry and you wanted to drink faster, you could punch a hole at the bottom and just take it in. That's one way to drive the flow. And in this problem, they are essentially punching two holes. Let's not worry about the second hole for a second. Okay, we are just asking the question: as soon as you punch the hole, what will drive the flow? What will cause the flow to jet out?
Atmospheric pressure.
Is it only atmospheric pressure? What about the weight of the liquid that's above this hole, above the level of the hole?
That would as well.
That would cause the flow to come out, right? The whole point of punching a hole at the bottom is to have the weight of the liquid above to push it through, right? So the more the depth, the higher the flow rate is going to be. Number one. Number two, forget the second. Let's just look at the top one here. You punch a hole here. Is the flow rate going to be constant until the liquid is empty, or until the liquid comes to the height of the hole? Is the flow rate going to be constant over time? Why not?
Less,
Less.
much less weight.
Exactly, as the fluid drains out, the driving force gets weaker and weaker until it just goes away. So after the liquid level drops below this height, there is no more flow, right? So any estimate that you do is only driven by the instantaneous height of the liquid above that level. Okay, so now your question or task is, what is the flow rate of oil density given from this tank, from this first hole, which is at 10.5 centimeters below the liquid level at the start? It won't be there forever. Okay. Having said that, now if you remember in the fluids project of trying to measure the flow rate in a nozzle, in a funnel, you can now think of what will be the height level as a function of height. If you master this problem, you are ready to do part of your project. Okay. So first, how do we solve the problem? We may not have time for the entire thing.
We're only doing the DR, or are we doing DR and DT?
Let's just talk about DT, just the first topic. How will you set up the problem? From here to here, so let's call this point 1, and we'll call this point number 2. So we can identify a streamline that would go from here until here. So you're applying Bernoulli between the top level and at the exit. Is that what you're saying? Thank you. So everyone is clear what's the starting point? You apply Bernoulli equation between the top surface and a point on the exit cross section. Okay. Is that a question?
Yes, would you do the point at the top all the way to the left or all the way to the right? Or like somewhere that doesn't matter?
It technically doesn't matter because you know that pressure only depends on height. So if you think of the top surface, you consider the top surface to be at rest, in the sense it's moving very slowly compared to the exit, that whatever fluid velocity is over here, we effectively consider that to be zero. So it's static fluid at the top. So any point that is at the same level is at the same pressure. So the choice of whether the point is labeled here or here at the center, it's not important. That answer your questions. Okay, so you identified 2 points. One is at the top surface, one is at the exit. So you apply the equation between point 1 and point 2. Okay? We still have 5 minutes. Let's do this. Does everybody have a picture? We good? If you want details, I'll provide. So we have our tank. Okay. And we are only considering one exit, one hole right now. Don't worry about the other. Let's just focus on learning this first. This is the level, and we consider a point 1 here and consider a point 2 here. And we'll draw a streamline that connects 1 and 2. Just to tell ourselves that these two have to be on the same streamline. Unless if it's a heavily viscous fluid like oil or soap or something, that's generally true. But if this exit flow is turbulent, it's not necessarily true. So we'll talk about turbulence at the end of towards the end of the class, okay, towards the end of the course. Okay, so P1 plus half rho V1 squared equals P2 plus half rho V2 squared. Everybody is okay? I just didn't even write about gravity, which is the height difference here is like 10.5 centimeters. I made an engineering judgment that over 10.5 centimeters, the height difference is not important. Okay. See, that's bad practice. I can do that because I'm not the one taking the exam, but you are the ones taking the
Yeah, I
exam.
was just about to ask how would we put that exam?
So we'll write rho g V1 equals P2 plus half rho V2 squared plus rho g Z2. So we can write Z2 minus Z1 is 10.5 centimeters. Okay, so we can write rho g delta Z is neglected compared to other terms. If you do the calculation, it will turn out to be a really tiny number. That's why I'm neglecting. Okay. So we are dropping this. What else can we drop? What else can we do to simplify this equation? Do we know V1?
No, bro.
We know rho. Okay. That's a known, so you can punch it in. Do we know V1? Okay. V1 is in reality, V1 is not exactly 0, but V1 is taken to be 0 approximately because why? Because sorry,
Start right.
the top surface moves very slowly compared to this fluid because the top surface moves slowly compared to the fluid exiting at 2 compared to the fluid exiting at 2. So we think V1 is much smaller than V2. So we'll just say V1 is approximately 0. Yes,
If we were to write this another way, like the flow rate and the area and velocity,
yeah,
if we just show the difference in areas, would that all?
brilliant. Brilliant, yes, that's correct.
Okay.
So what he's saying is, if you consider this to be an area A1, and you know that Q is the same, is equal to A1 V1 equal to A2 V2. What he's saying is V1 is small because A2 over A1 is small.
Even would be the atmosphere, right? And
P1 would be atmospheric. Here we come to that. I need to pick up pace. P1 will be atmospheric pressure and P2 would be atmospheric pressure plus the density of the fluid here, which I think is some oil, so we call it rho naught. Rho naught G delta Z. Rho naught G delta Z. Sorry, I should not have done this. We still have a role for delta Z. Okay, so the interest of time, I'm going to write P atmosphere equals P atmosphere plus rho G delta Z plus half rho V2 squared. V1. Yeah, I think I made a sign mistake, but I think you understand that half rho V squared should be equal to rho naught G times 10.5 centimeters. I made a sign mistake. I'll fix it at the end of at the start of the next lecture. But if you go through this, you're going to get V2, from which you can get Q is equal to A2 V2. Okay, I'll fix it next lecture. Please do the practice problems. Please take a look at the mock exam and start your preparation
when is the exam again?
next Tuesday.
Next Tuesday.
Next Tuesday. Okay, come talk to me if you want to. Thank you. Yeah, please bring your sheets. Actually, hold on. Keep it because this will be good material for you to revise for the exam. Okay, I'll give points to everyone who. Keep your sheets.